Hello students, starting with your class on module 4 which talks about your virtual memory. Before we get into detail with your virtual memory, probably in the introduction of your operating system, we tried to understand what is virtualization. What do I mean by virtual? Virtual is something that is not real. We are creating an illusion that it exists. The same applies with your virtual memory. So I am creating an illusion that there is sufficient memory that exists, but in reality that is not the case. Last chapter we saw about your main memory, that is, for me to execute my process, the process need to be brought into the main memory, and also the main memory is limited. I cannot be accommodating too many processes in my main memory. Now, I think as a student, you're working with a very limited number of program size and you're generally not very concerned about the memory. But as a student, you develop an application or a project, definitely you will have concerns about the memory usage. You will also optimize your code for less memory usage. Now, when this is the case, why can't I give the programmer the liberty to not think too much about the memory and he could freely code? Now, what do I mean by that? Now, in reality, there is a lot of physical memory that is required for that process or program to execute. But with the help of virtual memory, I create an illusion to the program or user that the sufficient memory is available that could accommodate his program or process, but that does not exist in reality. Now, how am I able to create this illusion? When I started the discussion, I said, if a process need to be executed, the process should be kept in the main memory. But the question lies in, should I need to have the whole program in the main memory? That is where I am able to create this illusion. Now, there are some error conditions. If the programmer does not encounter, or if the user does not encounter that error condition, that error routine is never used. Then why should I give space to that error routine in my main memory? There are some array and list allocation that happens. Now, if I ask you to write a program to print your name, you would say an array of 50 or 55, whereas your name requires only around 15 to 18 characters. So you can see that there is so much more memory that is allocated. And there are some features or there are some options that are there in an application or a program that is rarely used. But even that code will be brought into the main memory, which is not necessary. So what is the technique that we are talking about here is, we bring in the code only that is required, or we bring in the code only that is executing at that current instance of time, rather than bringing the entire code at the beginning. Now, doing so, that gives several advantages. More programs could be run at the same time. because every program is partially bought into the memory, and each program is consuming a very less memory that eventually leads to many programs could be accommodated in the main memory. And now the programmer also could write larger code without bothering about the address, and there are less IOs would be needed to load, swap your programs into memory. So here is the technique of your virtual memory. Now what does virtual memory say? It is a separation of user's logical memory to physical memory. Students, if you remember, last chapter that we saw about your main memory management, any technique that we saw, we had a clear one-to-one mapping with the logical memory and the physical memory. So if I have to just give you a recap, if I was dividing the logical memory into pages and physical memory into frames, if I had 5 pages, I would have equally 5 frames. So there was a clear one-to-one mapping that was happening between your pages and frames. That will not be the case in case of your virtual memory. Only a part of the code that is needed shall be brought into the memory. And the logical address space or the virtual memory could be much more larger than the physical memory. Here is a small illustration. Now if I require page 0 to page N or page V, I am not putting all these pages into the physical memory. I am putting only the required pages into the physical memory. The other pages shall remain on the hard disk. Whenever it is required, only then I will be swapping that into the main memory. Virtual memory also allows files and memory to be shared by several processes through your page sharing, which we have addressed in the last chapter. Now, how do I implement this virtual memory? There are 2 techniques of implementing your virtual memory. One is demand paging and the other one is demand segmentation. So the logical address space of the virtual address space of a process refers to the logical or the virtual view of how a process is stored in the memory. The physical memory may be organized in a page frame, but it is not contiguous. You can notice it here. So we have already seen the memory allocation techniques. You had contiguous and non-contiguous. Definitely the virtual memory can be supported with your non-contiguous memory allocation. A little more variations to the same is where we are able to implement your virtual memory. Now every process has an address structure or every process has a memory structure. Now here also the virtual address space is used as a stack or heap that can grow inside. So I think when we started with the introduction of your process, you have seen this structure. The same is what is replicated here. So this is the virtual address space which a process tells that this is the amount of memory. 0 to max is, for example, if process 1 tells I need around 5 or 10 MB to complete my process. So 0 to 10 MB is the actual, it is the virtual address space that a process needs. But are you really allocating 10 MB in the main memory? Not really, but you give an illusion to the process that 10 MB is actually allocated. So that is about your virtual memory. Now, how is it implemented? When we started the introduction, we told there are two techniques. One is demand paging, the other one is demand segmentation. Now, let us address to the first one, that is your demand paging. Now, what happens in demand paging? It is similar to your paging system, but it also includes the technique of your swapping. Now, what happens here? A process shall be kept in the secondary memory or the hard disk. The process is brought into the main memory only when a process wants to execute that part of the code. We also call it a lazy swapper. Now, just to on a lighter note, when do we say a person is active or lazy? An active person is usually moving around. A lazy person moves only when it has an utmost requirement. So here also the swapping is done only when that part of the code is required, rather than swapping or rather than bringing the whole content into the main memory. So what happens by doing so? If I, rather than bringing the whole 10 MB, for example, I am only bringing what is required, it could sometimes be only 50% of the memory. So there is less memory needed, less IO operations, faster response, and there could be more number of users who could be using the main memory. Now, so as I just told it to you earlier, so all the pages that are required would be on the secondary memory. Only the pages that are required shall be brought into the main memory. So how do we do it? The page that is needed shall be referenced. If it is an invalid reference, we probably treat it as an illegal action. If it is a valid reference and it is not in the main memory, probably you swap out some other page and you swap in that page. Now let us see how do we do the same. We do it with the help of your valid and invalid bit. If you remember, in the last class we had discussed about your protection. So during the protection we spoke about this valid and invalid bit. So the protection there, it was referring to the paging mechanism which tells that the process is referring to a legal address space that is allocated to that process. If it is trying to access a address space or a page that is not allocated to that, then we were calling it as invalid. The same thing applies here, but invalid has a little more variation to that. If there is a page that is marked invalid, one, it could be actually illegal or invalid. It also could be that the page is not in the main memory, but it could be on the secondary storage. Now what happens? In the paging mechanism, we maintained a page table. So in the page table, we had the frame numbers, and along with the frame numbers, we had the protection bit of valid and invalid. So this scheme is going to distinguish whether the page is on the disk or it is in the main memory. If it is valid, the page is in the disk. If it is invalid, it could be in the secondary memory. If it is not in the secondary memory as well, probably the process is actually trying to access another process memory. So initially all the bits are set as invalid. So illustrating the same, as I told you, if the bit is valid, then it is legal and it is also in the main memory. If the bit is invalid, either the page is not at all valid to the process, or it is valid but it is currently not there in the main memory. Now let us see here. So as I told you, this is the logical address space or the virtual memory that a process is asking for. So it totally has 8 pages. So page 0, page 1, page 2 to page 8. Now if you remember to what was the paging mechanism that we saw earlier, all these 8 pages were mapped to the frames. So there was one-to-one mapping that was happening. Now what are we doing in your virtual memory scheme? We are not mapping all the 8 pages to frames, but we are mapping only the frames that is required. The remaining are in the hard disk or your secondary memory. Now take a look at it. These are the page numbers. These are the pages, the content. Now here I have the page numbers, and then I have the frame number, and then the valid and invalid bit that is a part of your page table. Now in the physical memory I have the frame number, and then I have the content, and this is my secondary memory. Now let us see. I have page 0, the content is A. So the page 0 is at frame 4 and it is telling it is valid. Yes, it is in the main memory. Now let me see page 1. Page 1, the content is B. Now if I go to page 1, I don't have any frame assigned to page 1. It is showing it is invalid. Now the operating system will immediately check in the secondary storage. Now I can see that the content B is there in the secondary storage. So it is a valid address, but probably it is not available in the main memory. Now if the process needs B for execution, then the swapper is going to swap this content B to the main memory, and the bit will also be changed from valid to invalid. When a page is required and the page is not present in the main memory, we call it a page fault. So during the address translation, if the valid and invalid bit is set to 0 and if that page is required, then probably we are faulting, and that is about your page fault. We will see further what is your page fault and how we could be resolving the same. Now what is a page fault? As I told you, if a page is needed but it is not loaded, it is not available in the main memory at the very first reference. Now for the very first time I am trying to execute the content B, but the content isn't there, it is marked as invalid. So it is a fault. The page is not available is a fault. So that is the concept of your page fault. Now having said about the page fault, let us see how the page fault works. Here is the illustration of the same with the step-by-step procedure. So the first procedure, it is going to check whether the memory address requested is valid or invalid. So when it is seeing to that invalid, it raises a trap to the operating system. Now, the operating system is going to check whether it is a legal address or an illegal address. If it is a legal address, then we will have to check it should be there in the secondary memory. If it is an illegal address, probably the process shall be terminated. Now, when it is a legal address, the page should be there in the secondary memory. Now the step 4 is where it is going to bring that page from the secondary memory to the main memory. So to bring it to the main memory, it has to look for a free frame in the free frame list. After that, the disk operation is scheduled to bring that page from the disk to the main memory. After the page is loaded to the main memory, then probably there should be changes that should be made to the page table by setting its reference in the page table and also making this invalid bit to valid. And then finally the instruction can start its execution, or if there is a data, then the data can start its usage. So this is how a page fault is handled. Now there is another concept that we have, that is your pure demand paging. Now what is it about your pure demand paging? A page shall never be, if there is a process, the process shall never be allocated the main memory at all. So once it starts the execution, it starts with faulting the page. So it starts the execution, it needs the very first frame that is not available, it is going to fault, and now that page is brought to the main memory, it is executing. After the completion of that execution, it needs another page or another chunk of code, so it again faults. So pure demand paging is every page that is required by a process to execute shall be faulted, and only then it is brought into the memory. It starts the execution without loading any page to the main memory. That is your pure demand paging. Now there is another issue that is there which we will have to address. Now we were talking about bringing a page, we will have to get a page that is there in the secondary memory to the main memory. Now what if main memory is full? What do we do? How do we allocate? Now see this same scenario. Here we said we will find a free frame from the frame list and we are going to allocate. Now I did not find a frame that is free at all. What do I do? That is when we talk about your page replacement. That is one of the concepts that you have in the coming topics. So what is about page replacement? We will be finding a particular frame in the main memory which could be replaced, that is, which could be swapped out, and we bring in another page which needs to be executed. There are various algorithms, and each algorithm has its own benefits and liabilities. We will see what are the algorithms, and we will also see which could be the best algorithm that could be followed. Now what is the support of hardware we have for the demand paging? So it is now, what is demand paging? It is a combination of the concepts of your paging and swapping. So in the last chapter we have already seen what is the hardware support for paging, that is what is the page table, what are the various page table structures and all that. So here what is required by the hardware is to have a page table and your secondary memory. So using the page table we could be doing your paging, and using your secondary memory is where it is going to help us to swapping. That is, whichever particular piece of code or a page is required shall be swapped into the main memory. Now let us see to the performance of your demand paging. Now, is demand paging really very good? Now, is it a very good thought that to bring in the page only when it is required? Let us see how it could be checked. Now the performance of the demand paging can be checked with the page fault rate. 0 to be the lowest and 1 to be the highest. There could be a range or a percentage in between. That is, there could be 40% of page faults, or there could be 20% of page faults. So if it is 0, it is considered as no page fault. If it is 1, it is considered as 100% page fault, which we discussed the concept of your pure demand paging. Now how do I calculate the effective access time? This is the formula that is used. 1 minus P. P is your page fault rate or the ratio into the memory access, then page fault overhead. Now what is the page fault overhead that we have? Whenever a page is going to be faulted, there is probably a list of activities that happen internally to the system. We have seen some of it already in the illustration of your page fault. The same thing when it is a little elaborated at the system level, there are a lot many activities that happens. For example, it is going to generate a trap. For the first time it faults, and then we have to check, is the trap interrupt generated for this page fault only, or is there any other thing for the trap is generated for? And after that we have to determine whether it is a legal address space or an illegal address space. And after that we have determined, we have to check if it is in the memory, and then we have to read from the disk and write here to the main memory. And when there is context switching happening, probably we have to save the process state that is there. We have to be writing memory, so many registers are saved, so many registers are rewritten, and there we need to restore the registers, and all these activities need to be done. Now if virtual memory or the technique demand paging is giving us a set of advantages, but also it comes with certain disadvantages as well. So whenever we perform demand paging, it is directly proportional to the page fault. So you can see the effective access time here. It is directly proportional to the page fault rate. So it is important to keep the number of page faults low. If the number of page faults increases, then I have already told the number of activities that is involved in the page fault. So each of these activity is definitely going to incur some amount of time, some fraction of a second. each of it adding on will eventually delay or bring down the performance or the response of your process. So it is always better to have less number of page faults. So we have to have a balanced act where we are also saving the main memory and we are also trying to have a good response of the process. The next thing that we have is about the concept of your copy on write. So virtual memory has one of the benefits in the process creation. Now when I say it is a process creation, the process is created using your fork. So there could be a parent process and an associated child process. Now this parent process and child process could be sharing the pages. We started the discussion of your virtual memory with the concept of separating the user's logical memory and physical memory. In the introduction itself I mentioned, so making this separation, it brings us another advantage where several different processes could be sharing the pages. Now let us see how it happens with the parent and the child. So what is the concept here? So as the name suggests, it is copy on write. So there will be a copy created when there is a write operation that happens. So what happens here? Initially the parent and the child is sharing the same page, and these pages shall be marked as your copy on write pages. If a process tries to write something on this shared page, a copy of that shared page shall be created. Now let me illustrate the same. So you can see here, now if I call process 1 to be the parent process and process 2 to be the child process. Now both the parent process and the child process is working on 3 pages ABC. This structure can continue until process P1 and process P2 is just reading the contents of A, B and C. Now if one of these process tries to change the content or modify or try to write to this page, then probably there is a copy of it that is created. Now you can see here the process 1 and 2 was sharing these 3 pages. Now when process P1 tries to write something to the page C, we are creating a copy of that page C, and now the process 1 will be seeing to this copy of the page C where it is modified or it is written with the new value. Now process 2 continues to see the old one on which it is working, and process 1 will be looking to the new version which it is modified. Now what is the benefit I have by doing the same? If there was no page sharing that happened, probably I would have to allocate 3 pages for process 1 and 3 pages to process 2, and I would have ended up spending 6 pages on both the process that is working on the same content. Here I would be saving that. I would only be occupying a space to something that is modified and something that a process is exclusively working on. If both the process ends up just reading the content, then probably I would not have to make a new allocation. If one of the process wants to modify any of the content, so that modified content shall be allocated a new frame from the free frame list.